Okay, we are going to start Unit 7 today. Our first topic is states of matter. A lot of what we talk about here will be review from previous science classes that you've taken, but we'll be going into a little bit more depth about these topics, so let's get started. So, as you can see here, and as you've probably learned in a previous class, there are three states of matter. These are also called the three phases of matter. The one over here on the left, where all the particles are clumped together, in this case, they're all in a cube type shape, that is a solid. They have a definite shape and a definite volume, and it doesn't matter what container you put it in, they're going to keep the same shape. When all of those particles kind of collect at the bottom of their container and are all together, but are also free to move, is a liquid. And over on the far right, where the particles take up all the space, all the volume in a container, that is a gas. We're going to watch a quick little video clip here about the kinetic molecular theory and what that has to do with the states of matter and how the particles behave.
The kinetic molecular theory is the theory that all matter is made up of atoms and molecules that are always moving. These particles hold kinetic energy and move around in random directions. In higher temperatures, the particles have high energy, and in low temperatures, the particles have less energy. The more energy a particle has, the faster it will move. In solids such as ice, the particles hardly move at all and hold a regular pattern because the energy is low and the particles are tightly packed. In liquids such as water, the particles have more energy and the freedom to move around. Liquids have the ability to flow and fill the shape of any container they are put in. In gases like steam, the particles have the most energy. These particles are sparse and move around freely. Gases are usually invisible to the eye and they can be expanded and compressed in different pressures. All matter is composed of atoms and molecules that are always moving. The higher the temperature, the more energy these particles have. And that is the kinetic molecular theory.
So in class, we watched the video and then we had an opportunity for students to share out some important things from the video. So really some key ideas are that the higher energy molecules move faster, and what that really means about them is that they are at a higher temperature. So the particles are always moving in random motion, and the higher the temperature, the faster they're going to move. So this idea of the molecular motion is called the kinetic molecular theory. This says that atoms and molecules are constantly in motion, and we measure the energy of the movements as the temperature of the substance. So the more kinetic energy a substance has, remember kinetic energy is the energy of motion, the more molecular motion there will be, and therefore the higher the perceived temperature will be. What does all this mean? What it really boils down to is this phrase that I like to say, heat 'em up, speed 'em up. If you heat up molecules, they are going to move faster. If you can remember that, you're on the right track. So we are going to fill in this chart that we have using the next slides. So you have this chart in your notes. We're not going to show exactly what this chart is on the next slides, but we're going to have information about solids, liquids, and gases. We're going to think about, do they have a definite shape? Do they have a definite volume? How are their particles spaced? How are their particles moving? And you can draw a little sketch. So to start, solids are matter that have a definite shape and a definite volume. So the solid pictured here on the right is showing us that the molecules are very close together. And as you can see, those molecules are barely moving, if they're moving at all. They do not move past each other. They just vibrate in place a little bit. So it's kind of like students sitting in their desks during class. Everyone is like staying in the same place, but you might, stretch your arms, you might be writing, you might be looking around. So you're not perfectly still, but you're staying in the same place. That is what a solid is like when we look at the molecules. Solids are not easily compressed because the particles are very, very close to each other already. They have a very rigid shape and structure. Liquids. All right, so liquids are this middle picture here. And if you look closely at where my pointer is showing you, those particles are not still. They are sliding past each other. They are moving around a little bit. So liquid is matter that has a distinct volume. It has a certain size, but it doesn't have a specific shape because the molecules have that freedom to move. The molecules and atoms are close together, but they have the ability to slide across one another very easily. They are not locked into place. Liquids are more compressible than solids. That means that you can push the molecules closer together to make up a smaller space, but they're still not very easily compressed because the particles are very close together to begin with. Their shape will change as the container changes, and their structure will remain the same. So if you pour a liquid from a graduated cylinder, which is tall and skinny, into a beaker, which is short and squat, the liquid will change its shape. It will now take the shape of the beaker, but it's still the same amount of water. It's still the same volume. Finally, we have a gas. A gas is represented by the picture on the left here. A gas is matter that has no fixed volume or shape. It completely conforms to the volume and shape of its container. Its molecules or atoms are very far apart from each other and they move very quickly. Gases are very easily compressible. That means that you can squish them into a smaller volume. And gases will always take on the shape of their container while their structure is the same. So they will take on the shape of their container. All right, so if you need to pause here and get that information, this is a summary of the last 3 slides. Feel free to pause here, get this information, and then we'll continue on. All right, so because solids and liquids and gases have different particle spacing, they're going to have different density. So if you consider all 3 phases of matter, the following rules hold true for most substances. Solid is more dense than liquid. That means that the particles in a solid are going to be very close together. Liquid is more dense than gas. So liquid is kind of medium. And then in a gas, the particles are very spread apart from each other. And again, we see that in this diagram here. In a solid, the particles are all in a very small space. And so that represents a high density. When they're spread apart, that's a very low density. Now, one exception to this fact is water. Water does not obey the rule about liquids and solids. For water, the most dense state of matter is actually the liquid. So a liquid water sample will always sink when compared to a solid. This is why ice floats. So in this little diagram here, we have a polar bear floating on an ice sheet. This is really what happens. Because the ice is less dense than the water, it will float on top and the water falls to the bottom because it's more dense. This is an unusual exception to the rule. Again, remember, usually solid is the most dense. All right, so we're going to take a little jaunt over here to a website where we are going to look at this simulation. So I'll keep this pulled up here while we do the simulation. The simulation is showing us the different states of matter and how different variables such as pressure and temperature and what the substance is can change it. So starting out, this simulator has given us the substance, neon. Each neon atom is a little blue circle. So what state of matter is it in and how do you know? So look at it for a minute. What state of matter do you think that this neon is in? Are the particles sliding past each other? Are the particles floating freely? Or are they kind of locked into place? Well, in this case, the particles are locked into place. So the answer to that first question would be that the neon is in the solid state of matter because the particles are locked into place. They are not moving except slight vibrations. Question 2 says, what happens to the neon particles as I apply heat? Answer in terms of the state of matter and the speed of the particles. So I'm going to change the temperature by adding heat, and watch, it shows a little fire there. Ooh, so when you add heat to those neon particles, well, remember, heat them up, speed them up. So what is happening here? That neon has changed, and now those particles are free floating in all directions. They are not confined to the bottom of the container anymore. So what state of matter happened, or what state of matter have we created? It is now a gas. So it is a gas, and we know that because the particles are moving faster and more freely, and they are not connected to each other anymore. All right, next up, number 3, what state of matter is water in? We're going to change to water. Okay, and so it changed the temperature for us. It set it the way that we want it to. So what state of matter is the water in, and how do we know? I'll let you look at it for a second. Well, because the water particles are floating, flying freely through this container, that would be a gas. We know that, again, because the particles are moving in straight line motions in all directions, taking up the full volume of the container. Question 4 says, what happens to the water particles as I cool them? So let's see what happens. We're going to put some ice in there. We're going to cool the temperature way down. Notice how the particles are starting to stick together. Okay, those gas particles, when they hit the particles down there at the bottom, begin to, again, stick to them. They're not floating freely anymore. The particles begin to stick together. That would be the liquid state. Oh, now something interesting has happened. Now they're not even sliding past each other, really. Now they're locked into place. So as they get locked into place, that would be a solid. We know that because they are no longer sliding past each other. They are stuck in place, and they are simply vibrating a little bit. All right, so that is our experiment here. So again, if you'd like to pause, feel free to, so that you can get a complete answer, but it's basically what we just talked about. Okay, a little bit more on the different states of matter. Solids, there are 2 different types of solids. They're basically organized solids or disorganized solids. So the first type is called a crystalline solid. These are molecules that are packed very tightly together in a very predictable way. They're arranged in a very orderly geometric 3-dimensional structure, and the smallest repeating part of it is called a unit cell. Amorphous solids, on the other hand, the particles are not arranged in a regular repeating manner. So we're going to pull up a picture real quick of crystalline versus amorphous. All right, this is a wonderful illustration. So a crystalline solid, like we have here on the right, we see that all of the particles are always arranged in this hexagon shape. Because it's regular and repeating, that is a crystalline solid. Amorphous, on the other hand, there is no pattern of how these blue and green atoms are linked together. It's very random, very disorganized, and so that would be an amorphous solid. So those are our 2 types of solids. Now liquids. We have some key vocabulary about liquids. Liquids have this property called fluidity. Now liquids and also both gases have the ability to flow. So if you imagine pouring water from a watering can, it just pours out the side. It doesn't like flow upwards, you know, it always flows downward. And it does not just stick together in the watering can. It flows out. If you have that flowing motion, that is called fluidity. Viscosity is the measure of the resistance of a liquid to flow. So it's like, how flowy is it? All right. Cold pancake syrup is very, very resistant to flow. It is very viscous. Other examples would be things like molasses or honey or shampoo and conditioner. These are very viscous liquids. Water, on the other hand, like coming out of the shower or coming out of a watering can or your kitchen faucet, it flows very easily. It has a low viscosity. Now, viscosity decreases with temperature. If you heat up the syrup in the microwave, it will pour easier. If you heat up shampoo, it will be more liquidy, it'll pour easier. So temperature can affect viscosity. The final little tidbit on liquids is something called buoyancy. Buoyancy is the upward force of a liquid that keeps things afloat. So if you imagine that you're floating in the water, it's a peaceful summer day, and you're just doing a back float in the pool. Well, shouldn't you be falling? Gravity is pulling you down. Why are you floating at the top of the pool? Well, water has an upward force that keeps you afloat. All right. Next up, we have 6 transitions between the 3 states of matter. Some of these are probably familiar and some of them are new. Please take a moment to pause, write them down, and then continue. The changes between solid and liquid are probably very familiar to you. You can imagine ice melting, or water freezing, okay? Liquid to solid is freezing, solid to liquid is melting. Gas to liquid is also probably a little bit familiar to you. A liquid to a gas is called vaporization. So if a puddle disappears on a hot day, the water vaporized. Condensation, just like what you talk about on the side of a cold glass of ice water, that's called condensation. That's the gas in the air becoming a liquid on the side of your glass. So condensation. These two, on the other hand, sublimation and deposition, are probably new to you, so I would circle them. Sublimation is the change directly from a solid to a gas, and deposition is the change directly from a gas to a solid. We'll look at some examples of these, but this is just the definition. And again, make sure you circle sublimation and deposition. I guarantee you those will be on the test, and those are the ones that you've probably not heard of until chemistry. Now, those phase changes involve a change in energy, because in order to change from one state to another, let's say from solid to liquid, which would be the melting change, well, the particles either have to gain energy or lose energy. To go from a solid to a liquid, the particles have to move faster. That means they have to gain energy. So the 3 phase changes that involve an increase in heat are going to be melting, vaporization, and sublimation. All 3 of these involve a change in heat in which the particles move faster. All 3 of these would be called endothermic changes. Endo means into, and so all of these involve heat going into the substance. On the other hand, what 3 phase changes involve a decrease in heat? Well, it's kind of like freezing. How do you freeze something? You take heat away from it. So, freezing, deposition, and condensation all involve a decrease in energy. They all involve the particles moving slower. If we decrease the heat in a substance, that is called an exothermic change. Remember, exo means out of or outside, and so the heat is being transferred outside. Okay, this is a crucial concept to understand. Are phase changes physical or chemical, and why? Well, when we talk about melting or freezing or vaporizing something, is it the same chemical in the end, or did we create a new chemical? In this case, it is the same chemical. If you freeze water, it is still water. It's just solid now. So all of these phase changes are still water. Okay, there's water molecules in the solid state, water molecules in the liquid state, and water molecules in the gaseous state. So because we're not creating a new chemical, these are all physical. So here is our answer. Phase changes are physical changes because the chemical's identity and structure does not change. The molecules simply move faster or slower, but they remain the same chemical. If we changed what chemical it was, that would be a chemical change, and that would be a completely different topic. All right, So in class, we took some time to find real life examples of all the different phase changes. You can probably think of some real life examples of melting and freezing, but we tried to get more creative. So here are some examples. And again, feel free to listen up to all of these examples and then pause to take time to write them. Melting, ice melting to water. That's a very boring example. But another interesting example would be candle wax. Candle wax is going to melt when you light the candle, so that would be melting. Freezing. Ooh, someone in class came up with this great example of freezing. When bacon grease is left to cool to room temperature, it's going to congeal and it's going to turn into a solid. So liquid bacon grease turning into solid when you leave it out at room temperature is freezing. Candle wax, when you blow out the candle wax is going to solidify. That is also freezing. These are two great examples because they showcase that freezing does not have to mean cold. Freezing simply means going from a liquid to a solid. Vaporization. A puddle is warmed on a hot day and it gets smaller. Or water boils on the stovetop and turns to steam. One of the examples that we had in class is after you mop the floor is wet, but then if you wait a couple of minutes, it's dry because the water has vaporized. Condensation. When water droplets form on your bathroom mirror when the shower is on, if you take a hot shower and you come out and the mirror is all steamed up, that's condensation. Literally the water from your shower vaporized, but then when it hit the cold mirror, it liquefied again. That's condensation. Or water collecting on the side of a cold drink can, especially on a hot, humid summer day, you're going to get a lot of condensation. Okay, deposition. Humidity in your freezer can cause frost on food or surfaces in your freezer. That's sometimes called freezer burn, okay? Or if frost forms on a car on a cold morning. If it didn't rain, but you have frost on your car, that means there was no liquid. So that must be deposition, straight from a gas to a solid. Sublimation is from a solid to a gas. So solid air fresheners, they get smaller over time as they release their fragrance into the air as a gas. Or ice cubes can shrink in the freezer. If you leave them there for like a year, an ice cube will get smaller and smaller and smaller. That's sublimation. Or dry ice, which lets off CO2 gas. It is literally dry because it skips the liquid phase. It is a solid dry ice cube and it turns into carbon dioxide gas. All right, so that is it. If you were absent for class, check in and see if you have an assignment over this topic. And that is all. I hope this was helpful and I'll see you on the next video. Thanks for watching. Bye.